Let's continue our discussion of stereochemistry. This is Stereochemistry 3, Part 2. Here we've got 1-bromo 3-methyl cyclohexane, and you'll notice it has two asymmetric carbons that are indicated by the asterisk, one here, one here. Because the compound has two asymmetric carbons, it has 4 stereoisomers. They are asymmetric because they are bonded to 4 different groups. Notice 1, 2, 3, 4. 1, 2, 3, 4. In the slide where the arrows are pointing, indicating these two groups are different, means that the carbon is also bonded to 2 different carbon-containing groups, which are here and here. They're different from each other. 2 enantiomers can be drawn for the cis isomer, and 2 enantiomers can be drawn for the trans isomer. We're using cis and trans because of the ring structure that exists. Here's the 2 asymmetric centers again, resulting in the 4 different stereoisomers. We have cis 1-bromo 3-methyl cyclohexane and trans 1-bromo 3-methyl cyclohexane, where these groups are on opposite sides of the plane of the ring. Here they're on the same side. The methyl group and the bromine group are on the same side. Now if we were to draw 1-bromo 4-methyl cyclohexane, you might do that. Draw 1-bromo 4-methyl cyclohexane. So now we've got the bromine group here, that could be 1, but 4 position, 4-methyl would have the methyl group over here on this carbon. So write that down and visualize it. Does it have any asymmetric carbons? No. You should be able to see that it does not. Therefore, it only has 1 cis isomer and 1 trans isomer. In fact, with 1-bromo 4-methyl cyclohexane, you'll see that the carbons that are bonded to the 2 different carbons are actually not asymmetric, but they're the same. Therefore, the carbon at these locations that we would suspect as being asymmetric are not asymmetric. Okay, so a little bit of practice helps. Okay, let's go to the next slide. Meso compounds. Okay, by definition, a meso compound is recognized by 2 or more asymmetric carbons in a plane of symmetry. Key definition: plane of symmetry and 2 or more asymmetric carbons must be present. If a compound has a plane of symmetry, it will not be optically active even though it has asymmetric carbons. A plane of symmetry cuts the molecule in half, and one half is the mirror image of the other half. A meso compound is achiral because it is superimposable on its mirror image. Mesos is the Greek word for middle. When a compound has 4 atoms or groups bonded to 1 asymmetrical carbon that are identical to 4 atoms or groups bonded to the other asymmetrical carbon, then the compound has a stereoisomer that is a meso compound. It will have only 3 stereoisomers. One will be a meso compound, and the other 2 will be enantiomers. So it's actually 2 raised to the 2nd power minus 1 when a meso is present. So we only have 3 stereoisomers that result. Now remember that we said the maximum number of stereoisomers a compound within number of asymmetric carbons can have is 2 to the n. Notice that's maximum. In this case, it's not maximum, but that is the maximum that's possible if a meso were not present. So here we have a plane of symmetry, and we have 2 meso compounds. Notice the asymmetric carbons have the same 4 groups bonded to them. So we have one of these as a meso. We call it a meso compound. They are achiral molecules. Okay, let's look further here. In the case of cyclic compounds, the cis isomer will be the meso compound due to two asymmetric carbons and a plane of symmetry being achiral. And the trans isomer will exist as enantiomers. So here we have 2n minus 1 being 3. So we got 1, 2, 3. Also, 2 raised to the n minus 1, because we have a meso, equals 3. 1, 2, 3 enantiomers, stereoisomers. Now, we have to look at this clearly. Here is the plane of symmetry. Look at that very closely to make sure you understand that cis-1,3-dimethyl cyclopentane has a plane of symmetry right where it's drawn. Here is an asymmetric carbon and also one right here. Okay? And here's trans 1,3-dimethyl cyclopentane. Notice that they are across from each other or on opposite sides of the plane of the cyclic part of the molecule. Here is again a plane of symmetry, two asymmetric carbons, one right there, one right there. Therefore, it's a meso compound because each one of these is bonded to the exact same 4 types of molecules or components of the, or groups are bonded to the asymmetric carbon. And again, here's trans 1,2-dibromocyclohexane, a pair of enantiomers, where the bromine, the 2 bromine ions are on different sides of the ring. So those are some examples of meso that you need to be kind of on the lookout for. Okay, as long as one conformer of a compound has a plane of symmetry, the compound will be achiral. And just for illustration, here is various components, various examples that you can see. As you know, a chair conformer is on the left and a boat conformer is on the right up here. Again, if the achiral compound that has a plane of symmetry has 2 asymmetric carbons, then it is a meso compound. Here, there is no plane of symmetry, so there's no possibility of a meso compound. Here we do have a plane of symmetry, and here we have no plane of symmetry illustrated in a staggered conformer. Here's an eclipse conformer where there is a plane of symmetry that's drawn and shown here. Okay, that concludes our second part, Stereochemistry 3.